Systems, Professor Schulz from Chemistry Culture.
Ladies and gentlemen, we believe that in Fischer Tropsch chemistry, the abundance of products, of many products, because it's an ordered composition, gives the message for what is going on the surface, what the surface reactions are. And so far, we are much concerned with the detailed composition of the reaction product. Therefore, initially, I'd like to present just a little part of the chromatogram.
More behind you.
Then you see the major compound, the alpha-olefin, you see 10 fraction, you see the smaller amounts, trans 2-DC, cis-2-DC, with a double bond in the second position, and a very small amount is a double one more internally in the chain. And then you see some branched olefins in red. Then you see the black hydrocarbons, the saturated paraffin, and here the monomethyl branched ones. And then you see three compounds, three series of oxygenates. One series that the N-alkanols, the other series with the ketone, astonishing with the ketone, and the other one with the aldehyde. And these are the three series we observe, and this just as an example. The slides. The slides.
Right there. By the table, huh?
First line. That's now the outline of this small talk. The objective of investigation, the experimental part is the reactors, catalysts, parameters, sampling, analysis, evaluation of results, then some results and discussion, ideal and real kinetic schemes and models, transient systems during the starting conversions, differential carbon balances, differential selectivities. Then a little about aldehydes, alcohols as primary Fischer Tropsch products, if there are some ones, and branching probability of branching regularities within the system. Next one. Our experimental points here in this lecture now are, we have used fixed bed reactors and the CSTR reactor slurry phase. Then we have applied several catalysts, two iron catalysts mainly, one manganese modified, the other copper modified. Manganese is good for primary selectivity, copper is good for lowering the reduction temperatures, but otherwise they don't affect the selectivity not so much. Reaction parameters, 250 degrees, 310 degrees centigrade, 5 to 20 bars, time on stream measurements, then product sampling. There we use particularly our special method, sampling in small reactivated glass ampoules, total gas vapor sample streams from the stream, and these will bring to the analysis. This saves much labor, and this yields us a time resolution of less than 1/10 or 1/100 of a second. Then we sample of the hot gas vapor product stream, and when we get in these samples representative compositions C1 to C17. Then the quantitative evaluation is we add neopentan to the exit stream, and we add as well in a well-known amount nitrogen, and so we may now calculate from the chromatograms directly the yield of individual hydrocarbons, their formation rates, as well as the consumption rates of CO, and so on. And so far, then the analysis, that's a high resolution chromatography, temperature program from C1 to C20 mainly. Composition groups then accordingly to compound type and carbon number. to be concerned a little with the Fischer Tropsch system. It's often quoted as a polymerization reaction. This is very true, but this is only one part of the total. And one shouldn't forget that in principle a very complicated system. There's very many additional things being of importance. For instance, if you want to add one monomer to the chain, then this needs chemisorption of one CO, formation of fourth chemisorbed H, splitting of the CH bond, formation of a new CC bond, transfer of 2H to the carbon atom, transfer of 2H to the oxygen atom. And these are 11 elemental steps of surface reactions. These are associated with chain prolongation by only one CH2. And many of them are not directly accessible of these reaction steps to kinetic measurements as they proceed in the chemisorbed state. And so far, I regard this as a unique example of chemistry in 2 dimensions. And I like to use the title of Gauss-Schumacher's book for this. And this, of course, then has an extremely high content of information about its rules. So now when regarding the building of the models of building the hydrocarbon chains, there's the ideal system which had been in 1946 been established by Harrington, and this is very much similar like in the homogeneous phase. And so far it's very useful, but it's on a very gross approach. And a real system then has to take into account that these growth steps, they may be all carbon lambda dependent in rate constants. On the other hand, that there is a branching possibility from each surface species, and that there are desorption product formation possibilities for a paraffin, for an olefin, for an alcohol, and for an aldehyde as well. We have developed this system quantitatively, and we use it mainly now to calculate these individual reaction rates of the individual compounds and of the individual steps, and now to understand the system from the numbers, from these regularities of these constants we derive from experimental compositions. So this is the concept I just said. We use this to calculate reaction probabilities, rates, rate constants of elemental reactions for real Fischer Tropsch systems from precisely determined product distributions which are not scrambled but secondary conversions of products. This is now my first result in this connection. The time axis, that's the starting of the experiment, and the ordinate, these are fractional carbon streams. The 100%, that's the total of carbon coming in with the carbon monoxide. And here, for instance, the organic compounds as carbon, they are equal to the yield of hydrocarbons and as well to the activity of the catalyst. And so we see now that for this catalyst, that's an iron manganese modified catalyst with some potassium, that we see in the initial stage the catalyst is little active. The activity only increases, is created in the early phase stage of the experiment, and it needs some 2 days until we reach quasi-stationary state of activity. This is at 250 degrees centigrade, this is at 370 degrees centigrade. We come to the higher value of activity here at the higher temperature as to be expected at an earlier time of only a few minutes. We can then discriminate that we are missing here a lot of carbon. This is the total carbon. This is the unconverted CO, that's the CO2. That's what we are missing to the 100%. And that's due to losses of carbon. That is due to deposition of carbon on the surface, and it's due to wax. Wax selectivity is not very high here. It's a little bit less than this. And so far, it mainly reflects now deposition of carbon on the surface. And we can see that there are two periods or two sorts of carbon deposition. there's an area of fast carbon deposition here in the first 10 to 15 minutes or so. Here it's very fast. And then we have a slow carbon deposition which goes on for 1 or 2 days. And in this system, it appears to us that the first is a reconstruction, a reordering, rearrangement of the surface or close to surface catalyst. And on the other hand, the other is more a bulk phase rearrangement in our system. Next one. Well, then the conclusions are creation of the dynamic Fischer Tropsch system with iron manganese potassium. Full stationary activity is obtained only within 1 or 2 days. 2 ranges of carbon deposition can be discriminated. Fast deposition, the first one, half up to 1 hour, corresponding to surface and close to surface reactions. Slower deposition lasting 1 or 2 days, corresponding to bulk phase conversion of the catalyst. At low temperature, 250 degrees, the near to surface catalyst rearrangement and coverage is a major process. And it needs a relatively long time. At high temperature, 310 degrees, quasi-stationary activity is obtained faster, and excessive uptake of carbon in the catalyst lasts for 1 or 2 days. The active sites of Fischer Tropsch CO hydrogenation are only formed during the initial steps of an experiment. Their number, their nature changes with changes in experimental conditions. Here this concerns selectivity for the same 2 experiments. 250 degrees centigrade, 310 degrees centigrade, the time axis logarithmically given, and here percent of the different things. Percent here for chain prolongation. This is the stationary state some 70% at 310 degrees. At 250 degrees, the probability of chain prolongation some 80%, it's higher. Then the fraction of alpha olefins within the N-olefin fraction C4, it comes to a stationary value of some 95%. That's the primary product, but we don't obtain the primary product initially. There's only some 65%. We see the same here, the olefin here at the higher temperature. It's only to a small amount the alpha olefin, only after some time we come to the primary Fischer Tropsch product. And we see as well olefins in C2 because C2 is very sensitive, the ethylene, to a secondary olefin hydrogenation. And so far, that's very much suited to regard secondary olefin hydrogenation. We see as well the value of olefin content in C2 increases from slow values initially to high ones of some 80% after a relatively long period. And we see a fast change in the first 10-20 minutes, and we see slow changes when lasting over 1 to 2 days also. Next minute. This is another time on stream: 3 hours, 51 hours, 75 hours, 144 hours, 168 hours, 168 hours. Time on stream measurement, and it shows on above carbon number of the compounds the alpha olefins among the N-olefins. And this is the primary selectivity. The 95% alpha olefins we obtain only here after 170 hours or so. And initially we have only a small amount of primary olefins, and the slope or the pattern of these curves is that with increasing carbon number, that the faster secondary conversion of these alpha olefins via hydrogenation or via double bond shift. So the conclusion is chain prolongation probability increases with time on stream. Secondary olefin hydrogenation is inhibited with time on stream then, and secondary olefin double bond shift is inhibited as well. Yeah. This concerns now the alcohols and the aldehydes. These are these Anderson plots, I'm sure to call them. The Anderson plots over carbon number, logarithmic moles of the linear linear hydrocarbons or the linear alcohols, the linear aldehydes, and the sum of both for 6 hours, 22 hours, and 129 hours time on stream. And it turns out that a large part of this curve here and this curve here, particularly after longer reaction times, is in parallel to the sum of aldehydes and alcohols. Initially, the alcohols are more than the aldehydes initially. However, finally, they become more or less in parallel. We know this from many other experiments. It's a little difficult to make precise measurements there, and we then conclude from this, because these are parallel lines, that also the aldehydes, the sum of both, are primary products of the reaction as well as the hydrocarbon, and that also the alcohols and the aldehydes both are primary products of a reaction. So these conclusions then are in more detail. In most Fischer Tropsch systems, secondary conversion of aldehydes and alcohols is obscured. Their role is then not known, cannot be derived from these experiments. Fischer Tropsch products with primary composition of aldehydes and alcohols have been obtained with iron manganese potassium catalysts. The molar logarithmic distributions show parallel lines for linear aldehydes and linear alcohols. This proves the primary nature of aldehydes and alcohols, because secondary reactions do yield different distributions which are not polymerization-like. This is very important, because secondary reactions do yield different distributions which are not polymerization-like. The molar logarithmic distribution of aldehydes and alcohols are parallel lines to those of linear hydrocarbons, indicating their formation through the same intermediates, more or less. For the investigated system now, the following values of reaction probabilities of the chemical intermediate of carbon number NCA were obtained. The values are given now in percent. The 80% for linear growth, 2.2% for branched growth, then the desorption reaction as an olefin, the 11.6%, as an paraffin, the 4.5%, as an alcohol, the 1.3%, as an aldehyde, the 1.5%. Yeah. This is my last item. It concerns branching. Branching reaction, we have derived branching probability as a function of carbon number, and it was quoted by Anderson in his early work that branching probability is independent of carbon number. If one derives these figures from actual product compositions, then one sees that branching probability as a function of carbon number is strongly dependent on carbon number, and a typical pattern of a curve is like this. A relatively small value for the first branching probability, a high one for the next, and then an exponential decline. And these are for different situations in Fischer Tropsch chemistry, but we see here another pattern for branching probability. Here the first branching probability is higher than the second one, and then the other ones are very low. This pattern is relates to a composition, to a situation in Fischer Tropsch chemistry when there is a strong steric demand at the surface around the active sites. Then these things become controlling. All branching is very slow, and the branching is only possible for the first situations, in the first smallest members of the homogeneous series. Yeah. And if we plot now logarithmically branching probability over carbon number, then this proves the exponential decline of branching probability over a broad range. So, to conclude this point, probability of obtaining branching is seen to be strongly dependent on carbon number. An exponential decline from the second possibilities possible step is observed for a major range of conditions. The first step of branching is governed by separate rules. Branching probability, that's what we think, is regarded as a measure of degree of demanding spacious restriction at the active sites, because any imaginable branching reaction will need more space than linear chain growth. I want to go with this. Thank you for your answer.
I'd like to explain the picture.
Oh, excuse me. Franz Fischer. I wanted to have Franz Fischer in the room as well.
Okay, any questions? Yes,
Developmental research. Could you contrast the activity of your iron precipitated catalyst without magnesium, or manganese to your manganese precipitated catalyst? And also, could you contrast the water gas shift activities, relative activities there?
Yeah. Water gas shift activities normally associated with iron catalyst and needs mainly the potassium, and I think in most systems it's not a Fischer Tropsch reaction, but it's as well working within the system, and in many cases it just consumes all the water which is being produced, and you have an equal effect from smaller amount of CO2 also. That's in most of the systems.
There's no inhibition by the manganese support for activity?
No, not now.
How are absolute activities compared to CNS rate space velocities?
Activities between which?
Activities per gram of iron, say, space velocity for 50% conversion.
I can't give you precise numbers. I couldn't look into the files for that. Basically, the manganese, when added in small amounts, increases activity. But finally, if you have more and more manganese, then the catalyst, that even as related to iron, becomes less active. That's what we found.
Those alcohols at such high carbon numbers.
It inhibits strongly secondary reactions.
Well, if I have no further questions, thank you very much. And we'd like to thank all the speakers for this morning's session, and close the session now, and I think we'll start.